In this lecture, we'll take up some examples to better understand the idea of span, basis, and dimension. In the lecture prior to this, on the topic of span, basis, and dimension, we studied for two vector spaces. One was the vector space R2 over the field reals, and one was the vector space of 2 cross 2 real matrices again over the field reals. For the vector space R2, we considered three finite sets of vectors, namely x1, x2, and x3. And we saw that the vector space R2 is essentially a span of x1 and a span of x2 and a span of x3 as well. But as we move into the definition of basis, we additionally, in addition to the span, we needed that the set of vectors to be linearly independent. And this was satisfied by the sets x1 and x2 and not by the set x3. Hence, x1 is a basis of R2 over the field of reals. Similarly, x2 is also a basis for the vector space R2 over the field of reals. And it's not true for x3. Also, for the real matrices, we consider two sets of vectors, namely set x1 and x2. x1 could span the vector space and consist of linearly independent vectors, while x2 does not have linearly independent vectors and still spans the vector space. So, by definition, x1 qualifies to be a basis. The dimension was said to be basically the cardinality of the basis. In the first case, for the vector space R2 or field reals, the cardinality of the basis is 2 and hence the dimension of the vector space is 2. Whereas for the 2 cross 2 real matrices vector space or the field of reals, the cardinality of the basis is 4 and hence the dimension of this vector space is also 4. We also made a note that a vector space does not have a unique basis associated with it, but the dimension of the vector space is unique to it. So the dimension of the vector space is unique to a vector space. Now, when I say vector space, I am also basically attaching the notion of field along with it. Okay. So let's take up a few more examples and understand these ideas of span, basis, and dimension. So let us consider a polynomial of set of polynomials of degree 2. Define it as x of t such that x of t is equal to I equal to 0 to 2 alpha I t to the power I, where alpha I belong to reals. Okay, so the field is considered to be a set of vectors. Note that these alpha i's are actually the scalar component on this particular field. Okay, now consider the set, let's say x1, where the basis, not the basis, let's say that it is 1 and t. In this case, is this true? Is this true? So how do you verify? Let there be a vector represented by x that belongs to the span. Please note that we are trying to show a set equality. Span of 1t is a set, p2 is a set. We need to show the set equality. So let's check whether this is true or not. X belongs to a span of 1t, which essentially implies that x can be represented as let's say alpha 0 plus alpha 1t, where alpha 0 and alpha 1 belong to R. R is the field. And this implies back that x belongs to E2. So this is true for all x in the span, which essentially means that you started basically from a vector in the span and you ended up showing that it is going to be a vector in P2. So essentially showing this, that the span is a subset of. Now let's take a vector in P2. If this is a vector in P2, I can represent x as some beta 0 plus beta 1t plus beta 2t square, where beta 0, beta 1, beta 2 belong to the field R. Note that if beta 2 is not equal to 0, then x does not belong to the span of one of the set of vectors 1 and t, which implies that E2 is not a subset of the span of the set 1 and t. So P2 is not spanned. Okay, so X1 does not span P2. Consider another set for the same vector space where we take it as 1, t, and t square. So again the question is this true? I'll skip some steps here, but essentially what you can show is for all x in the span of x2, you can represent x as alpha 0 plus alpha 1t plus alpha 2t squared, where alpha 0, alpha 1, alpha 2 belong to R2, and this would imply that x belongs to P2, which implies that the span of x2 is a subset of p2. It looks like I didn't skip any steps. Similarly, for all x belonging to the vector space p2, x can be represented as beta 0 plus beta 1 t plus beta 2 t square, where beta 0, beta 1 plus beta and beta 2 are in R. Let me correct this. This is R. Okay. Now essentially this implies that x belongs to span of x2, which implies that p2 is a subset of span of x2. We have already established that span of x2 is also a subset of p2. So both of them together, so these two together imply that p2 is basically equal to the span of x2. So the set x2 spans the vector space p2. Similarly, let us consider another set of vectors, which is let's say 1 t and 1 minus t square. We'll put the same question, that is p2 spanned by the set x3. So for all x belonging to the span of x3, I can express x as alpha 0, alpha 1 t plus alpha 2 1 minus t square. For alpha 0, alpha 1, alpha 2 in the field, which is essentially equal to alpha 0 plus alpha 2 plus alpha 1 of t plus minus alpha 2 t square. This essentially means that x belongs to the vector space p2. This is true for all x in the span of x3. So span of x3 is a subset of p2. Now let's show the other way also, that p2 is a subset of span of x3. Let's check whether that's true or not. So for any vector that you take from the vector space p2, it can be represented as beta 0 plus beta 1 t plus beta 2 t square, where beta 0, beta 1, beta 2, all of them belong to the field which is reals. Now this can be expressed as, let's say, beta 0 minus some gamma this is alpha beta 0 plus some gamma, by mistake, plus beta 1 of t plus or sorry, rather let's break it. in this form. Let's break it in this form. That gamma plus beta 0 dash plus beta 1 t plus minus of gamma t square, where gamma beta 0 dash belong to R and gamma is equal to minus beta 2. If I do this, what I get is beta 0 dash plus beta 1 t plus gamma 1 minus t square, and this is implying that x belongs to the span of x3, which implies that p2 belongs or is a subset of the span of x3. So both these relationships together establish that p2 is equal to the span of x3. Similarly, you can try to show that if this is the set x4, then p2 will be a span of x4. Similarly, if you consider another set which is x5, you can show that p2 is a span of x5. Okay, so now we have considered 5 different sets of vectors, non-zero vectors, namely x1, x2, x3, x4 and x5. Now let's start with x1. So what we are going to do is, for all these 5 sets, we are going to check whether each of them form a basis or not. Okay, and once we find our basis, we will come to know about the dimension of the vector space as well. So let's start with x1. Since p2 is not spanned by x1, so x1 cannot qualify as a basis. So x1 as a basis is ruled out. What about x2? x2 p2 is being spanned by the set x2. Also, is the set of vectors 1 t t square linearly independent? The answer is yes. x2 is a linearly independent set. So what we have is, I'll add it here. Let me use a different color. x2 is a linearly independent set. So both these facts together imply x2 is a basis of a set of 2-degree polynomials over the field of reals. I request you to please verify whether x2 is a linearly independent set or not. And similarly, if you check for x3, x3 is also a set of linearly independent vectors. Okay, and the spanning and linear independence together imply that x3 is a basis of the set of second-degree polynomials over the field of reals. Now what about x4? This is not a linearly independent set. Similarly, x5 is also not a linearly independent set. Okay, so neither x4 nor x5 form a basis. Okay, so both of these are not a basis. They do not qualify as a basis. Now we know that x2 and x3 both of them qualify as basis. So what is the dimension of P2? It's the cardinality of the basis, and in this case the dimension turns out to be 3 because you need 3 linearly independent vectors to span the vector space P2 defined over the field of reals. Okay, so I'll say that the dimension of P2 is 3. Okay, here you can actually note one thing, that if the dimension of a vector space is n, then any set of n plus 1 non-zero vectors is always a linearly dependent set. Let me put it down. If dimension of a vector space is n, then any set of n plus 1 number of non-zero vectors, why should I say non-zero? Vectors are linearly dependent. Similarly, if you notice, there is one more uh, observation that you should have made is for an n-dimensional or let me put it this way. If dimension of V is n and a set of n non-zero vectors span V, then the set of vectors is linearly independent. Okay. Similarly, you can actually take up other examples. For example, let V be a vector space consisting of 2 cross 2 real matrices such that A equal to A transpose with the field being reals. You can verify that whether this is a vector space or not. Once you have established uh, that this is a vector space, and possibly you can take a set of vectors, let's say this set, please note that when we take the set find a set of vectors, it is always taken from the vector space itself. So the set of vectors is a subset of the vector space. Okay. Let's say that we have this set of vector. So here you can actually show that V is spanned by the set x1, and in addition to this, x1 is a linearly independent set, and these together implies x1 is a basis of V over R. Okay. Similarly, if you consider another set which is x1 union here also V is a span of x2, but x2 is a linearly dependent set, or it is not a linearly independent set. So x2 does not qualify to be a basis. Let us consider another set which is this. Here V is not spanned by the set x3. So this is sufficient to say that x3 is not a basis. What is the dimension that you have? Dimension of V. So if you look at x1 is a basis of V as we have established. So x1 has three linearly independent vectors. So the cardinality of x1 is 3. So the dimension of the vector space here is going to be 3. This dimension is unique to the vector space over the field of reals. Okay, but the basis x1 need not be. You can have another basis. For example, you can have a basis which is let's say x3 along with one more vector which is 1 1 1. So this x4 set is different from what you have in the x1 set. Okay, and you can verify that x4 is a linearly independent set, and also the vector space under consideration is spanned by x4, thus establishing that x4 is a basis of the vector space or the given field, which is reals in this particular case. Okay, now let's take up another example. Consider a vector space V, which is basically vectors formed by complex numbers. Okay, 2 cross 2 complex numbers. Sorry, not 2 cross. Vectors which have 2 tuples and the tuples belong to the complex. Tuples are complex. The field that I am considering is, let's say, set of complex numbers. Okay. Now consider a vector or a set of vectors which is one 0 and 0 1. For any x in C2, you can represent this as alpha 1 0 plus beta 0 1, right, where alpha beta both of them belong to the field, which is a set of complex numbers. This essentially implies that X belongs to the span of X1, which implies that C2 is a subset of the span of X1. Similarly, for all X belonging to the span of X1, you can show that X belongs to C2, which will imply that span of X1 is a subset of C2. So we essentially have that C2 is spanned by X1. Also, you can verify that X1 is a linearly independent set. So X1 is a basis of C2 over the field C, right? From here, what do you conclude about the dimension? The dimension does not change irrespective of the basis. So you have already established, you have already found out one basis. So as per this basis X1, dimension of C2 is 2, right? So other bases that you would find will always have two number of vectors. Okay. So if I take another set, let's say X2, I can represent it as 1 0. Let's say I am taking this, and to it where I is the imaginary factor. If I take this, yes, of course, the vector space is being spanned by X2, but X2 is a linearly dependent set. It is not a linearly independent set. Okay, so X2 is not a basis. Right. Now let's do this. We'll keep the same set V, but we consider a different field associated with it, and the field this time that we'll choose is the set of real numbers. X1 is 1 0 and 0 1, the collection of these two vectors 1 0 and 0 1. Will this be true? Is this true? Let's find out. Take a vector in C2. This can be expressed as a linear combination of vectors in C2 where the scaling factors are to be taken from the field. Okay, note that the scaling factors that are taken from the field are all reals. Okay, so what we have is, if X is of the form alpha plus I beta, gamma plus I delta, and I represent it as alpha 1 0 plus beta I 0 plus gamma 0 1 plus delta 0 I, where alpha, beta, gamma, delta, all of them belong to the field of reals, right? For x belonging to x1, when I define the span, again I have to take the scalars from the field. X will be some alpha bar 1 0 plus beta bar 0 1 with alpha bar beta bar belonging to reals. Now note that when beta is non-zero or delta is non-zero, x belonging to C2 does not imply that x belongs to the span of x1. So, in this case, C2 cannot be spanned by x1. Instead, if you consider the set x2, which is 1 0 0 1 I 0 and 0 I, you will have the vector space being spanned by x2. Also, x2 is a linearly independent set. Why? Because if you recall the definition of linear independence, the scaling factors that we were associating with each of the vectors and wanted all of them to be zero, so that the linear combination of them is zero, whereas in the zero vector, there the scaling factors are again from the field. Okay, so x2 is a linearly independent set. So both the spanning and linear independence essentially imply that x2 is a basis of the vector space V equal to C2 over R. Okay, I'll write it as C2. From here, what do you conclude? That the dimension of this vector space is 4. Now, if you compare this vector space, if you compare the vector space here, which is C2 over the field of reals, basically this is a real vector space, with the vector space here, which is the complex vector space. Though the sets under consideration are the same, it is C2, the field associated with them are different. For the complex vector space is the set of complex numbers, and for the real vector space is the set of real numbers. So these two vector spaces are entirely different vector spaces. Okay, the dimension of the complex vector space under consideration is 2, and the dimension of the real vector space under consideration is 4. Okay, so even though the vectors, the elements from the set C2 are same, the moment we attach the field is what gives you a complete notion of the completes the notion of vector space. Okay, so the former is the complex vector space, and the later, which is here, is the real vector space. Okay, one of them, the complex vector space under consideration, has the dimension 2, and the real vector space also under consideration has a dimension 4. Okay, so this example was basically trying to bring out the idea that the notion of vector space is complete only with the field that is attached to it. Okay. In the next lecture, we'll discuss something known as a subspace. So, similar to a set associated with a subset, here we'll try to find out a set or a subset from the vector space which preserves certain properties from the vector space and also satisfies some additional criteria. Okay, so we'll stop here. Thank you.